Quantum computing gets more hype than almost any technology in history. It'll break all encryption. It'll solve problems that would take classical computers longer than the age of the universe. It'll change everything. And then you look at the actual machines, and they're extremely expensive, extremely fragile systems that operate at temperatures colder than outer space, make errors constantly, and currently can't do anything reliably useful that a regular laptop couldn't do. So what's the truth? Is quantum computing real? Is the hype justified? And if so, when does it actually matter? Let me give you the most honest, clear-headed explanation of quantum computing you'll find. No physics PhD required. To understand quantum computing, you first need to understand what classical computing is, because quantum computing is defined by contrast. Classical computers, every laptop, smartphone, server, and calculator ever built, process information in bits. A bit is a binary value, 0 or 1, off or on. Every piece of data, every instruction, everything your computer does ultimately comes down to sequences of zeros and ones. When a classical computer solves a problem, it processes these bits sequentially, or in parallel across multiple processors, following logical operations. Addition, comparison, storage, retrieval, all built from this foundation. Classical computers are extraordinary. They can execute billions of operations per second, run incredibly complex software, simulate physical systems, and carry out tasks that would have seemed like magic to people 50 years ago. But they have fundamental limitations when it comes to certain categories of problems. Some problems are what computer scientists call intractable for classical computers. Not impossible in principle, but impossible in practice because the time required scales so catastrophically with problem size that even with all the computers on Earth running for the age of the universe, you couldn't solve them. These problems are where quantum computing enters. The core of quantum computing is the qubit, the quantum equivalent of a bit. Here's where we need to be careful, because the explanation is often oversimplified in a way that's actually misleading. The common explanation is a qubit can be both 0 and 1 at the same time. That's not quite right, and it leads to a lot of confusion. Let me give you the more accurate version. A qubit exists in a quantum state. When it's in superposition, it's in a combination of 0 and 1, but not literally both simultaneously. The state represents the probabilities of getting 0 or getting 1 when you measure it. Before measurement, the qubit is in this probabilistic superposition. When you measure it, it collapses to a definite value of 0 or 1. The power comes from how quantum operations can manipulate the probabilities before measurement, exploiting quantum mechanical phenomena to make certain outcomes more likely and others less likely, such that when you measure, you get the right answer with high probability. The second key phenomenon is entanglement. When two qubits are entangled, their states are correlated in ways that have no classical analog. Measuring one qubit instantly tells you something about the state of the other, regardless of physical distance. This correlation enables quantum algorithms to process relationships between large numbers of possibilities in ways that classical computers can't efficiently replicate. The third phenomenon is interference. Quantum algorithms are designed to make incorrect answers interfere destructively, canceling out, while correct answers interfere constructively, amplifying. It's like tuning a radio. You're adjusting the quantum system so the signal of the right answer becomes dominant. This is the section that most explainers skip, and it's the most important. Quantum computers are not universal replacements for classical computers. They are not faster at everything. For most of what a computer does, running your spreadsheet, loading a web page, streaming video, running AI inference, a quantum computer would actually be slower and worse. Quantum computers have an advantage for a specific set of problem types. Cryptography, Shor's algorithm. Peter Shor's 1994 algorithm showed that a sufficiently powerful quantum computer could factor large numbers exponentially faster than classical computers. This is a big deal because most of the encryption that secures the internet, RSA, relies on the difficulty of factoring large numbers. A quantum computer with enough high-quality qubits could theoretically break RSA encryption. This is why governments, banks, and the tech industry are urgently working on post-quantum cryptography, encryption algorithms that even quantum computers can't break. Search problems, Grover's algorithm. Grover's algorithm provides a quadratic speedup for unstructured search, finding a specific item in a large, unsorted database. Not exponential, but meaningful for certain applications. Quantum simulation. This is perhaps the most immediately practical application. Quantum systems are notoriously hard to simulate on classical computers because they're inherently quantum mechanical. The computational complexity explodes with system size. A quantum computer can simulate quantum systems directly. This means simulating molecules and chemical reactions with a fidelity impossible for classical computers, with profound implications for drug discovery, materials science, and chemistry. Optimization problems. Many industrial and logistical optimization problems, routing, scheduling, supply chains, financial portfolio optimization, have the structure that quantum algorithms might eventually be able to tackle more efficiently. This is an active research area with less certainty than the above applications. Let me be very honest about the current state, because the gap between the hype and reality is significant. Today's quantum computers are what researchers call NISQ machines, noisy intermediate-scale quantum computers. They have anywhere from a few dozen to a few hundred qubits, but those qubits are highly error-prone. Quantum states are extraordinarily fragile. Any vibration, temperature fluctuation, electromagnetic interference, or stray interaction can cause errors. This decoherence is the fundamental engineering challenge. IBM, Google, IonQ, D-Wave, Quantinuum, these are the leading quantum hardware companies, each taking somewhat different architectural approaches. Google made headlines in 2019 claiming quantum supremacy, demonstrating that their 53-qubit Sycamore processor could perform a specific calculation in 200 seconds that would take the best classical supercomputer 10,000 years. This claim was immediately contested by IBM, which argued classical computers could solve the problem much faster with better algorithms. In 2024, the state is, quantum computers can solve certain very specific, specially constructed problems faster than classical computers. They cannot yet reliably solve any real-world problem that a classical computer can't handle. The current machines are too error-prone, have too few quality qubits, and run for too short a time before decoherence destroys the computation. What's needed is fault-tolerant quantum computing, systems where quantum error correction allows reliable computation at scale. This requires thousands of physical qubits per logical qubit to run error correction. Getting to truly fault-tolerant machines is a challenge measured in years, not months. So when does this actually matter? The honest answer is that this is genuinely uncertain, and anyone giving you a specific confident timeline is probably overconfident. Near term, 0 to 5 years, continued progress in qubit quality and count. Some demonstrations of quantum advantage for specific scientific and optimization problems. Not yet breaking, encryption. Not yet transformative for most industries. Medium term, 5 to 15 years, potentially reaching fault-tolerant systems for specific applications. Real commercial value for quantum chemistry/drug discovery and certain optimization problems. First genuine threats to current encryption standards. Long-term, 15+ years. If the engineering challenges are solved, truly powerful quantum computers that could factor large numbers efficiently, simulate complex molecular systems, and solve certain classes of optimization problems at commercial scale. IBM has published roadmaps targeting fault-tolerant quantum computing by the late 2020s. Most independent experts think the timelines are optimistic, but directionally plausible. Microsoft is betting heavily on a different approach, topological qubits, which they believe could be inherently more error-resistant. Even if practical quantum computing is a decade away, there are real reasons to pay attention now. Post-quantum cryptography. The transition to quantum-resistant encryption standards needs to happen before quantum computers can break current encryption. NIST, the U.S. standards body, has already standardized the first post-quantum cryptographic algorithms. If you run any kind of digital security infrastructure, this migration timeline matters to you. Investment and opportunity. Quantum computing is attracting serious capital. The companies building the tools, algorithms, software, and infrastructure for quantum computing even the ones that are building quantum classical hybrid approaches, represent real investment opportunity as the field matures. Scientific impact first. The near-term impact of quantum computing will be in science before business. Drug discovery, materials science, fundamental physics research, these will feel quantum's impact first. If you're in those fields, this is directly relevant. Understanding technological disruption. Some of the most impactful technologies had long development curves before suddenly having enormous impact. Quantum computing may be on that trajectory. Getting ahead of the learning curve now, understanding what it actually does and doesn't do, positions you to recognize the genuine inflection points when they arrive. Quantum computing is one of those technologies that is simultaneously real, important, and wildly overhyped all at once. The physics is real, the potential is genuine, the current machines are severely limited, and the timeline to transformative impact is uncertain. The most important takeaway: quantum computing isn't a replacement for classical computing. It's a specialized tool for specific problem types that are currently intractable. When it matures, those specific applications, cryptography, molecular simulation, certain optimization, could be genuinely revolutionary. Like and subscribe to keep up with the technology developments that will actually shape the next decade. I try to give you the real story, not the hype. See you next week.